Acceleration can also be looked at mathematically as opposed to graphically. So I'm going to explain and I'll kind of walk you through the equation that we use. It's fairly straightforward. If you don't really like the graphing stuff, this will be, I think, a little bit easier. So let's first start with the definition of acceleration. So an acceleration is a change in velocity over time. It's the rate at which an object's velocity is changing. So if we use that basic definition, so speeding up, slowing down, changing direction, these are all ways we can change our velocity. As that obviously has to happen over some amount of time, that combination is what provides or produces the acceleration. So the equation that we have is essentially that the acceleration is equal to the change in velocity. That's what that little triangle delta means. The change in the velocity an object experiences divided by the amount of time it takes for that change to occur. Now we can go one step further. Anytime you're calculating the change in anything, in this case change in velocity, it's always the final value minus the initial. So if you know the object's final velocity, you subtract the initial velocity from that and then divide by the total amount of time over which that change occurred. So kind of give you the units and the variables and everything all in one place. The equation you'll be given is seen up above in purple. And the A stands for acceleration. The VF stands for final velocity. And as we've discussed previously, velocity is measured in meters per second plus some kind of direction. The VI stands for the initial velocity. Once again, meters per second plus direction. Those are just the two velocities at the two different points in time that we're analyzing. The initial velocity at the beginning of the motion, the final velocity at the end. And we're going to divide that by the time, which was t, as we normally know, is in seconds. Now you might see here that I intentionally left off the units for acceleration. This is a new variable, a new concept. So we have to kind of quickly look at this equation up top and try and figure out what the units are. You can certainly try pausing the video if you'd like to try and figure out the units yourselves. The answer can be found by analyzing that equation up top. But for those of you that don't want to try it, I'm going to use the equation up top. Acceleration is change in velocity over time, and I'm going to show you how you can use the equations to start to figure out what the units for these different variables have to be. So we know that the acceleration is calculated by dividing the change in velocity over the time that it takes for that to occur. So we also know that velocity is meters per second plus direction, those are the units, and then we're going to divide that by time, which has a unit of seconds. So if we look at that equation, but not in terms of the variables, in terms of the units for those variables, we end up with this weird unit, which is meters per second plus direction per second. Another way we can write that, and you might see it written this way sometimes, is meters per second plus a direction. Now you may see it like that on occasion. However, because it's seconds on the bottom and there's two of them, it's more commonly written as meters per second squared plus direction. So you'll more commonly see acceleration written as 4 meters per second squared, and then the south and north, depending on what the problem dictates. So this is a new unit. It's very similar to velocity, which is meters per second plus direction, but this is now meters per second squared plus direction. It's basically telling you how many meters per second of velocity you're going to gain or lose every second that elapses. So that's where that second squared comes from. It's how many meters per second of velocity per second of time that goes by the object is gaining or losing.